So our speaker today is Volodymyr Nekrashevych, and his talk, as you can see there, is on the simplicity of sister algebras associated with self-similar groups. Please, Volodymyr, go ahead.
Yes, thank you very much. Thank you very much for inviting me. It's actually the first time I'm giving talk on this paper. Let me give a short introduction. I guess you know all of this, but just to set up notation at least. So a groupoid is a small category of isomorphisms, and we identify objects with identity automorphisms and call them units. So if you have an element of the groupoid, the source of that morphism can be defined as gamma inverse gamma, and range is gamma inverse. And then you have two elements can be multiplied if the source and range of one is equal to range of the other in the natural way. So a topological groupoid is a groupoid together with a topology such that the operations are continuous, multiply with relative topology on their domains. And we do not require the groupoid to be Hausdorff, but we assume that the space of units, which I denote G0, is Hausdorff. Another notion is that of bisection. It's a subset of the groupoid such that the source map and the range map are homomorphisms. And the groupoid is said to be étale if it has a basis of topology consisting of open bisections. In other words, it's equivalent to say that the source and range maps are local homomorphisms. And okay, so in particular, étale groupoids are locally Hausdorff because we assume that the unit space is Hausdorff, so they are locally Hausdorff. And we'll talk about we'll talk only about étale groupoids. Moreover, we'll talk only about ample groupoids. So these are exactly the groupoids which are étale, and the unit space is totally disconnected, so zero-dimensional. Okay, so now Steinberg algebras and other types. So let's take a field, K. And so we say that a function, not necessarily continuous, any function from G to K is compactly supported if the set where it's not zero is contained in a compact set. And I will call this set the set of points at which the function is non-zero support, though usually they take the closure, but I don't take the closure because of the non-Hausdorffness issues. So I will call this support. Wait, how do I get out of annotation and go back to that place again? So suppose we have an étale groupoid, and let's say we have two functions such that one of them is compactly supported. Doesn't matter which one, but maybe both, but one will work. Then we can define convolution of these functions in the standard way. So you take the value of the convolution gamma is equal to the sum of these products, f1 of gamma 1, f2 of gamma 2, and gamma 1, gamma 2 is equal to gamma. And the fact that one of them is compactly supported implies that this is a finite sum. Just one being compactly supported is enough. Oops, how do I erase this? So now let's define the Steinberg algebras. If G is an ample groupoid, then we can take the algebra, so the set or vector space, well, it's enough to take, you can take it as a vector space generated by the characteristic functions of compact open bisections. And then it's easy to see that this vector space is actually an algebra with respect to convolution. All elements are compactly supported in the previous sense. The elements of this algebra are not necessarily continuous, because characteristic function of a compact open bisection might be not continuous, because a compact open bisection might be not closed. So this algebra, if the groupoid is Hausdorff, then of course every generator is continuous, and this will be exactly the algebra of compactly supported functions, continuous functions from G to if you take from G to K, where K is discrete. When G is Hausdorff, that's exactly the set of continuous compactly supported functions from G to K. But in the non-Hausdorff case, you can have non-continuous functions in this algebra, and that's the crucial point. Okay. Next, a classical construction due to Kohn. It's an L-analog. I mean, Steinberg algebras are somehow generalizations of this for arbitrary fields, but this is originally due to Kohn. You take the complex algebra spanned by, with respect to convolution, spanned by functions from G to C, which are compactly supported, and for which there exist open bisections containing the support of F, the support in the sense I mentioned, that you don't take the closure, and such that if you restrict F to U, the function is continuous on U.
Sorry.
So
may I ask one question?
Sure.
So if I take the discrete topology on C and apply the same definition, don't I get
exactly you get this?
Okay.
You get the Steinberg algebra. Yes. Exactly. That's.
I don't think so, because
no?
the Steinberg algebra, any function in the Steinberg algebra has finitely many values, right? So I think it's different.
Yes, but compactly supported. Wait, the support is in U. The support is compact. You have a map from U to discrete space.
With the discrete topology, right?
Discrete topology, you get.
Sure, sure.
Yeah, exactly. If you take discrete topology, you get Steinberg algebra. But in general, you get this algebra, which is much, much older construction by Kohn. Okay, so if we take the Steinberg algebra, so where C, you take this construction for discrete C, or you take this construction for usual topology on C, both of them will have, they will be complex involutive algebra, star algebras with respect to the usual star operation. Okay, so now let me define quickly the reduced C-star algebra of the group of a tile groupoid. This is particular to a tile. So if you fix a unit, you can consider the little L2. So I didn't explain this notation. You take the set of elements of the groupoid whose source is equal to X. So you take your point X and take all arrows starting from X. That will be a discrete set. And you take little L2 on it. And then if you take H, if H is in little L2, so if you take any function in this space and take its convolution with another function, so that this other function is on the left, then the result will be also function on the set Gx, on this set. And if one can check that, well, first of all, if f is compactly supported, this is well defined. As I mentioned before, in a convolution, you need only one function to be compactly supported. And one can check that for, one can check just considering the generators of the algebra, one can see that the result will be also in little L2. In fact, it's easy to check that the L2 norm of this as an operator is less than or equal to L infinity norm of the function f. So this will be a well-defined operator on this Hilbert space. So we get a representation, it's involutive, so you get a star representation, and now we can. So we get this family of representations. We can take the direct sum of all of them on X, and then the reduced C-star algebra is the completion of the consistent algebra of this analog of compactly supported functions with respect to the norm in this direct sum. Or in other words, you just take the supremum of the norms of these representations and fibers of the source map over all units. So that's the reduced C-star algebra. Another algebra which I didn't mention is the full C-star algebra. That's when you take all star representations of this algebra CC of G, which are bounded. So, and complete with respect to that norm. Now, another important fact, which is due to Jean Renault, as far as I know, that you can regard elements of the reduced C-star algebra as functions on the groupoid itself. With this definition. So you identify, so if you take an element gamma, then there is the source of gamma, x, and you take any function f, so you take the delta function at the source, so at the unit, f will move it somewhere, the regular representation. And, well, anyway, that's the formula. It's there is a natural way to identify, and this identification is identical on this algebra of CC of G. In the continuous case, in the Hausdorff case, this image of reduced algebra will be an element of C0 of G, so continuous functions vanishing at infinity. In the non-Hausdorff case, these functions might be not continuous. So suppose if G is ample, then as I mentioned, then this Steinberg algebra is a subalgebra of the algebra CC of G, and therefore of the completion. And it is actually dense, so you can define the reduced algebra starting from Steinberg algebra using the same definition as above, as on the previous slide. So instead of using the con algebra, you can use the Steinberg algebra, and you get the same completion, the same reduced C-star algebra. Okay, so now I'm closely approaching the. So suppose that we have a second countable étale groupoid. Sorry, I messed it. Then, as I mentioned before, the reduced C-star algebra, if you identify them with functions on G, by the way, I forgot to mention that Renault called this identification the J map. So this, then the functions are not necessarily continuous. In particular, you may have functions which are zeros almost everywhere. So you can have functions such that their strict support has empty interior. So the set of points where it's non-zero may have empty interior. So we denote this set of these functions this way, I essential of G. And it's easy to show that this is an ideal, is a closed ideal in the reduced algebra. In the ample case, we can define intersection with its intersection with the Steinberg algebra, and that's the algebraic essential ideal, or equivalently, it's exactly the set of functions in the Steinberg algebra such that their support has empty interior, so such that they are zero on a dense open set. So let me, I can just press this. It doesn't work. Yeah. So if G is effective, effective means that it is a groupoid of germs of some inverse semigroup of local homeomorphisms, or in other words, that if you have a unit which is I didn't define germs, but I hope that it's clear. So if you have a local homomorphism, so a homomorphism between open sets, a germ is its action around a point. So you identify two local homomorphisms if they act the same way on a neighborhood of that point. So effective groupoids are exactly groupoids of germs. Now, minimal means that its orbits are dense, and second countable, it's the same. So if you have effective minimal second countable ample groupoid, then one can show that this essential ideal is a maximal ideal, and such that the factor algebra is actually simple. This is in this the most general setting. It's a result of Kwasniewski and Meyer. It is a generalization, rather straightforward generalization of the old result of Jean Renault, claiming that in the Hausdorff case, the reduced algebra is simple. So if you think more, it's actually essentially the same proof shows that this factor algebra is simple. And the same is true for the Steinberg algebra. This is even easier than that, than Kwasniewski-Meyer. This is pretty straightforward. You just take an element which is not in the ideal, and you can show that you can multiply from left and right, and then take linear span and get the whole algebra. So, of course, now the natural question is, do we always have that the essential ideal in the sister algebra is closure? Because this algebra, by definition, the algebraic essential ideal is a subset of the essential ideal if you identify C of Steinberg algebra with a subalgebra of the reduced algebra. As far as I know, even with the recent papers that appeared, this is still open. You can correct me if I'm wrong. I don't think that there is an example where this is not true. Moreover, also, as far as I understand, it doesn't, it's not known if the fact that one is zero implies that the other is zero. There are better understanding than since it was before our paper. So now there is a new paper by Xin Li, Briggs, and Gonzalez, and Hume, and Lee, where they understand this better than our paper, so better than what I'm going to talk about. We'll talk about very particular class of examples. But as far as I understand, I know this is still open. And this is a little bit frustrating because this algebraic ideal, in principle, it's relatively easy to understand. And there are different, again, in this paper by these 4 co-authors, Briggs, Gonzalez, Hume, and Lee, they give some criteria of simplicity of this algebra, of the Steinberg algebra. And it's basically almost a problem in linear algebra. So if you understand very well algebraic essential ideal, and you know that the C-star essential ideal is its closure, then everything is fine. But in general, it seems to be not clear if it is the same. So I will talk about a particular class of algebras for which we know the answer to the second question. It's affirmative in the second question. Surprisingly, we still don't know the answer to the first question, even for our class of algebras, even though those algebras are pretty easy to understand. Okay, so now I'll define the algebras for which I will give the answer to the second of those questions. Again, I don't know the answer even in this class of algebras for the first question. So what are self-similar groups? Let X be a finite alphabet. And I'll denote by X star the set of all finite words over this alphabet. In other words, the free monoid generated by this set. A faithful action of the group on this set is said to be self-similar if for every element of G and for every letter, there exists another element, which I denote G restricted to X, of the group, such that G of XW is G of X, and then G restricted to X applied to W. So in other words, when you apply G to a word starting with X, you just act by G on X, and then you act by some other element depending only on X and G on the remainder of the word, so on the tail of the word. So if you continue doing this, you will. So now you apply this definition to this GX. You will see that then for every word there exists an element which I'll denote G restricted to V, such that if you apply G to VW, you will act by G on the prefix, and then you will act by this new element on the suffix. So in other words, the action is called self-similar if it combines very well with the shift, with the one-sided shift. So when you apply the shift, kind of when you conjugate, sort of, shift is not invertible, so it's not conjugation, but informally, if you conjugate the action of the group by the shift, you get again an action of the group. So action of element G by the conjugated by the shift gets again a new element of G. So this is the definition. Oh my gosh. So for example, the simplest non-trivial example is the odometer or adding machine. It's action of infinite cyclic group, so action of Z generated by an element A, which when it sees 0, it transforms 0 to 1 and then doesn't change the rest of the word. If it sees 1, it transforms 1 to 0 and then acts again on the word. So this is how you add 1 to a binary number. If you see, but this binary number is written in the other direction. So if you see 0, you change 0 to 1. If you see 1, then you change 1 to 0 and then carry. So that's the classical odometer. And you see that it is self-similar. Yeah?
So your alphabet consists of 0 and 1.
Yes, here the alphabet consists only of 0 and 1. Now remember, we have these new elements, which we call sections, G restricted to V. So we say that a self-similar action is contracting if there exists a finite subset such that if you take any element of the group, there will exist some n such that all these sections are in this finite set for all words of length n. So, for example, this action of the odometer is a contracting action. The point is that if you take a to the m and apply it to 0 w, you will get 0 or 1 depending on parity of m. If m is even, you get 0. If m is odd, you get 1. And then on the rest, you will act by a to m over 2. In this case, and a to m minus 1 over 2. In this case. So if you repeat it over and over, you will divide by 2, roughly. So at the end, you will get either identity or A inverse. So these are the only 3 possibilities that you will carry eventually. So this set, you can take identity A and A inverse as this set, and this will be satisfied. So this is called contracting, and contraction refers to the fact that these elements are shorter than G. So their length kind of contracts, they are simplified. So the smallest set n satisfying this condition, and that set will exist, is called the nucleus of the action. So contracting self-similar groups, they appear naturally as iterated monodromy groups of locally expanding covering maps, so they appear in dynamical systems. I don't have time to explain how and to define them. I just can say that the adding machine action, which I defined above, is the iterated monodromy group of the double self-covering of the circle. So if you take R mod Z and multiply angle by 2, you get a covering of the circle by itself twice. And the iterated monodromy group of this is exactly this adding machine. In fact, I had always a feeling that this is sort of Fourier transform situation, that the adding machine relation with the circle. And that's when I became interested in trying to understand this from the point of view of C-star algebras, this relation between expanding covering maps and iterated monodromy groups of self-similar groups. And there is a connection. It's not that nice. It is nice, but it's not really Fourier transform. It's something more complicated. I don't have time, but there is a way to explain this. But there is a way to associate C-star algebras directly with locally expanding covering maps. In fact, it existed in literature forever. For a long time, there is different authors did it in different ways. So if you have a covering of space by itself, you can associate with it, for example, a groupoid, and then associate an algebra, or you can construct a Kunz-Pimsner algebra associated with a covering map. There are definitions for branch coverings and so on. So it's a very classical subject in C-star algebras. You can associate a C-star algebra with these with covering maps. I will define for you groups, C-star algebras associated with similar groups, so iterated monodromy groups. And now, just by classification, we know that these algebras are the same. So the algebra associated with locally expanding maps will be isomorphic to the algebra that I will define for similar groups. But this isomorphism is through classification, through K-theory. It's not a direct isomorphism. So it is interesting to understand it deeper, but probably there is no natural isomorphism. I don't know. Okay. So in particular, this relation between the adding machine and this double covering of the circle is something very classical, which existed a long time. It's Bunce-Dedens algebra. And there are 2 different ways of defining Bunce-Dedens algebra. And these 2 different ways are exactly 1 through one can be generalized to self-similar groups, and the other is generalized to these dynamical, to these covering maps. Okay, just to give you one more example of self-similar group, you can take this iterated monodromy group of z square minus 1, which is a self-covering on its Julia set. And then the iterated monodromy group of that self-covering is generated by two elements. A acts like the adding machine, except for you carry B, not A. B doesn't change the first letter, and when it sees 1, it acts by A on the rest. So it's kind of delayed adding machine situation. So iterated monodromy groups are rather exotic objects. One big open question about contracting self-similar groups is whether they are all amenable or not. We don't know. We know that this for z square minus 1, this group is amenable, but the proof is not straightforward. It's rather complicated. So they are very interesting groups, very different from classical groups from geometric group theory. For group theory in general, it's very special class of examples. But they have very natural interpretation in terms of C-star algebras. So suppose you have a self-similar group, and I will denote it by G, X, stressing the alphabet, the role of the alphabet. So remember, in the definition, we had that the definition of self-similar group implied that if you have any group element and a word, then when you apply that group element to a word with that prefix, so G of V1 W, you apply G to V1, you will get V2, and then you will act by some other element on the tail, W. Now, we can identify words with transformations. So if you have a V, you can identify it with the transformation of appending V as a prefix. So this kind of creation operator. You multiply V, put V at the beginning. Then this equality that GV1 W is equal to V2 H of W for all W is actually can be written as this equality of transformations. That if you append V1, then apply G, that's the same as acting by H and then appending V2. So that's what. So we can do this rewriting. And now we can associate a C-star algebra with this just by imitating these transformations, so the group action of the group and action of words together using operators. So namely, we consider the following C-star algebra given by these relations. So we have the group is realized by unitary operators. So in the algebra, so we have generators are UG associated with the group elements and SX associated with the letters. So G mapped to UG is a unitary representation. So the other word, we take a copy of G in the algebra. And then whenever we have this equality, we have it inside the algebra. So in other words, if G of XW is always equal to Y H of W, you have that GX is YH. So we copy these relations inside the algebra. And then we add also Kunz algebra relations. So again, SX imitates appending X to the beginning. So if you append Y at the beginning and then erase X, if Y is different from X, you get 0 because you cannot erase X. Y is the first letter. But if Y and X are equal, if you append X and then erase X, you get identity. You get the same. And then if you erase X and then append it back, you get projection onto the set of words starting with X. So these projections add up to 1. So we define O of GX as the universal C-star algebra defined by these relations. There is another way of defining this algebra, which I didn't put on slides, but I want to mention that this algebra is actually a Kunz-Pimsner algebra. So there is the self-similarity of the group through these equalities. So Gx y is equal to yh. They define a natural structure of a Hilbert bimodule of a group ring in a way. And this is Kunz-Pimsner algebra of that Hilbert bimodule. Well, in fact, you can see it here. If you take the linear span of elements of the form Sx times UH, so UG or UG, if you take linear span of these operators, that will the group G acts on it from both left and right, and there is a natural structure of a Hilbert bimodule, Hilbert of this algebra generated by these unitary operators. So this is Kunz-Pimsner algebra. Okay. If the action is contracting, then in fact, you can reduce this to finitely many defining relations. I should mention that typically the contracting self-similar group is not finitely presented. So the adding machine is finitely presented, it's just cyclic group Z, but say the iterated monodromy group of Z square minus 1 is not finitely presented, so you cannot define the group by finitely many relations. And that's a typical situation for contracting group. But the algebra is finitely presented. So in this case, algebra is nicer than the group. So you can use algebra to find relations in the group.
But if the group is not finitely generated.
No, it's finitely generated, but not finitely presented. Yeah.
Okay.
Actually, the group itself does not have to be finitely generated. You can have infinitely generated group, but still the algebra will be finitely generated. Yeah, you can write group elements in terms of the algebra generators in some special way, and you will get, yeah.
Okay.
Now, this algebra has a groupoid interpretation. That's another way to define it. So you just take the group, because of the way it acts on prefixes. Its action on finite words extends by continuity to the action on the infinite words. And so the group acts on the space of infinite words, on the Cantor set, and also letters act on the space of infinite words in the same way, just by appending letters. And this is a local homomorphism. It's a homomorphism from X omega to its Clopen subset. So we get a semigroup of local homomorphisms, and we can take groupoid of germs of this inverse semigroup. So I'll denote this by G of Gx. And in fact, yeah, sorry, I didn't define it. So I did define, but it didn't read it. So we define the C-star algebra as the universal C-star algebra, but we can also define the star algebra as the complex star algebra given by these defining relations. So I define two algebras here. So the fact is that the star algebra is exactly those defining relations give exactly the Steinberg algebra of this groupoid. So that's an alternative definition of that algebra. And that C-star algebra is the full C-star algebra of this groupoid. So these are that definition with defining relations is is another way of to define these groupoid algebras. Now, if the group is contracting, one can show that this groupoid is amenable. So I maybe should say a couple of words. How? One can show that orbits, contraction implies that orbits have polynomial growth. And if orbits have polynomial growth, then you can use the standard argument to construct a to check Rayton's condition using the Cesaro averages of balls, or characteristic functions of balls. Those functions will be not continuous, they will be only Borel, but there is a trick due to Jean Renault which shows that if you take Borel functions in Rayton's conditions, you can get continuous functions. So in fact, you get amenability. And because of that, this algebra that I defined above with defining relations is actually isomorphic also to the reduced C-star algebra of the groupoid. Now, a couple of words about the structure of the algebra. This groupoid, so how the groupoid looks like. I said that it's groupoid generated by, generated by the action of the group and these maps. And because of self-similarity, what happens is that actually this semigroup, this inverse semigroup generated by this map, it consists of the following transformations. You erase a prefix, then you apply a group element, and then you append a prefix. So this inverse semigroup, it consists of such transformations. That you erase some prefix, you apply a group element, and then you append some prefix. So that's how this inverse semigroup looks like. So this groupoid is the groupoid of germs of this inverse semigroup. So in terms of algebra, it is written by this. I should have written it a different way, but anyway. And then we look at the amount by which we shifted. So erasing a word means that you apply the shift, and then you append a word, you shift forward. So if you take the difference of lengths of the words, that will tell you how much you shifted the word. The group doesn't change the length of words. So this is the change of length of words. Well, we are acting on infinite words. So it means that this is the shift, how much you shifted. And this is a continuous cocycle on the groupoid. So it's a morphism, homomorphism from the groupoid to the group. And it's continuous on the groupoid. And in particular, this implies that we get the associated gauge action, action of the circle. So it acts identically on the group part, and it acts exactly as the Kuntz algebra gauge action acts on the alphabet part. If you take the subgroupoid of germs of balanced transformations, so those that you erase a word of the same length as you append, we get a subgroupoid, which I'll denote this way. In many cases, actually, in most interesting cases, this is exactly the groupoid of the action of the group, of the germs of the action of the group on the boundary. So you don't need these to define it. In many cases, the group captures everything. And this is exactly the groupoid of germs of the action of the group. So this is precisely in terms of algebra, this corresponds to the invariant part for the gauge action. So this is, so we denote by A the convolution algebra, the C-star algebra of this groupoid, and it will be exactly the subalgebra of the first algebra of elements of fixed points of the gauge action. So this is gauge invariant part of the algebra. And there is the analogous part of the Steinberg algebra. Now, these algebras have another nice interpretation. So let's denote by D the size of the alphabet. Then the self-similarity will induce an embedding of the group into matrices. So let me explain this maybe better just on the example of the adding of the odometer. So you have that odometer acts on 0W by changing it to 1W. So it changes 0 to 1 and then acts by identity. And then it, and then it acts if you have 1W, you change 1 to 0 and then act on W by A. So you can write this as a matrix. So first of all, you see that you act on 0, 1 by the transposition. 0 is switched with 1. So you start writing the permutation matrix of this transposition. But now instead of writing ones in these entries, you write the action on the tails. So when 0 goes to 1, you have identity. So you get identity here. And 1 goes to 0, you act by A. So you encode action of A as this matrix. So you act by permutation on the first level. So you encode this, basically you imitate this by the permutation matrix. By then, instead of units in the permutation matrix, you write the action on the tails. So that's what I wrote in this formula. So that is called matrix recursion, and it was used in the study of self-similar groups for many years, even before C-star algebras. And now you can iterate it. So you have that A goes to 0, A, 1, A. Sorry, 1, 0. But now we can apply it again, the same formula. So here, 1 by 1 matrix became 2 by 2 matrix. Now this will become 4 by 4 matrix. So 0 becomes 0, 0, 0, 0. 1 becomes the identity matrix. This 0 becomes 0, 0, 0. And A becomes this matrix. So you get 0, A, 1, 0. And you continue. So you get 8 by 8 matrix and so on. So this is naturally done for every self-similar group. And so we get an embedding of the group ring into matrices, D by D matrices, D square by D square matrices, and so on. In fact, it's not an embedding. It's some homomorphisms. So there will be some non-trivial kernels. And this induces maps on the universal C-star algebras and the matrix algebras over them. And in fact, these two algebras, the gauge invariant subalgebras, are exactly the direct limits of these sequences. But in both categories. So this is, you take direct limit in the category of star algebras, or you take direct limit in category of C-star algebras, and that's this gauge invariant subalgebra. Again, you might recognize something classical in the case of the binary adding machine. When the group is contracting, in fact, the A0 is the direct limit of vector spaces over the nucleus. So it's finite dimensional vector spaces. Because everything is attracted to that finite set of cases, you can write it as this direct limit. And okay, so now the rest of the talk is a joint work with Eusebio Gardella, Ben Steinberg, and Alina Vdovina. So first, we want to understand the relation between essential ideals and first fact, which is easy, is that the essential ideals of the algebra and of the gauge invariant subalgebra of the Steinberg algebras are generated by the intersection as ideals by the intersection with this finite dimensional space. So everything is, all problems with essential ideal are actually in this finitely generated subspace. And so this comes directly from the fact that it's the whole algebra is limit of these, direct limit of these subspaces. And this is the main theorem. So let G of X be a contracting, let G, X be a contracting self-similar group. The following conditions are equivalent. The Steinberg algebra is simple. The C-star algebra is simple. And the intersection of the algebraic essential ideal with this finite dimensional space is non-zero. Sorry, is zero. That's that's a mistake. So the first step is we reduce everything to the gauge invariant subalgebra because the cocycle which defines the this subalgebra is continuous, generally continuous. So all problems with non-Hausdorffness sit in the gauge invariant algebra. In fact, these algebras are sort of extensions of the gauge invariant algebra by the shift, by Z in some way. So there are no problems with that extension. So all problems live inside the gauge invariant algebra. And then we have that then one of the main, like the central part of the proof is the following lemma, that if you have a contracting self-similar group with the nucleus, then for every group element and for every epsilon, if you take these okay, let me explain what these elements are. So you take words of length n and take this element. So what is this element? This element will be an entry in that matrix recursion. So you have your algebra A, you can write it, element A, you can write it as a D by D matrix. And then you can write it as D square by D square matrix and so on. You go all the way to D to the n, by D to the n, so to the nth term of this sequence. And this is this element is an entry of that matrix corresponding to the column W and row V. So the rows and columns are labeled by words of corresponding length, here length 1, length 2, and so on. In length n, they will be labeled by words of length n on the stage n. So this is a particular entry in the matrix. So the statement is that if you take any group element of the algebra, then the elements of the matrix uniformly approach this finite dimensional vector space. So this actually what contracting self-similar group, how the condition of being contracting plays here.
Sorry, is A the whole Steinberg algebra or the degree 0 part? Or
no, it's in the gauge invariant. It's in the gauge invariant subalgebra of the C-star algebra.
Okay.
So you take the C-star algebra and take the gauge invariant part, and then on that gauge invariant part there is still this sequence of matrices.
Mm-hmm.
In this case, these are isomorphisms because the gauge invariant algebra is the direct limit of those algebras. So this gauge invariant algebra is isomorphic to its own matrix algebra of size d by d, to the matrix algebras of d square by d square, and so on. So these maps are isomorphisms. And then you write a group element as corresponding matrix of size d to the n by d to the n. And the lemma says that the entries of this matrix uniformly approach this finite dimensional space. And so by this uniform convergence to this finite dimensional space, this is the key part of the proof, that if you have some non-zero element of the ideal, these entries uniformly approach this finite dimensional space, and you can show that they do not, if the element is non-zero, they cannot approach zeros. All of them cannot approach zero, so there will be always some element of this matrix which is away from zero, and it will be still in the ideal. And so you will find a non-zero element of the ideal in this finite dimensional space. And this way you get that everything is inside, all problems are inside this finite dimensional vector space. And then it is relatively easy to decide whether this condition is true or not. And this was done before by Ben Steinberg and Szakács. And they showed an algorithm, a simple algorithm, which decides this condition. And we improved this algorithm in our paper. But by now, there are also more general approaches to this question. Okay, that's all what I wanted to talk about.
Okay, thank you very much for a very nice talk.
Thank you.
Are there questions from the audience? Yeah, so I recently wrote a paper with two of the ordinary of the regulars of the seminar who happen not to be here today, Arnone and Mukherjee, on homology of groupoid algebras. And we looked into self-similar group actions on graphs, and we look. So there is this problem in that in the Steinberg algebra, that the group G does not necessarily embed into the algebra. That the GBs, I mean the group algebra, it does not necessarily embed. And
that's right.
Yeah, and one useful discovery that still to me is a bit mysterious, that we found, is that this is related to, is something that can be detected by looking in the degree zero part, that if something, so the nth term need not even be a sum of matrix algebras over the group algebra, because usually there will be some quotient, right? However, at the limit, it's the same. So if something in the group algebra will die in the Steinberg algebra, then it will die in the colimit.
Right. Yeah.
So so this I was reminded of this when you were explaining this restriction, but yeah. So I hadn't ever considered this contractivity on contractness property. So I'm I should think about how this
Yeah,
of
the
the
contraction
games,
property
yeah.
gives you this, that everything lives in the matrices of some finite dimensional vector space.
Mhm.
Yeah, but you're right. These algebras. So here I write the group ring. If you take the image of the group ring in this colimit, it will be very much different from the. For instance, if the group is contracting, this colimit algebra will have polynomial growth. So the image of the group ring will have finite Kirillov dimensions, so have polynomial growth. But the group ring will be something very different. Yeah, that's true.
And related to a question, to some problem you mentioned, that using classification, you could show that two algebras are the same because are isomorphic because they have the same K theory. So is that you are looking only at the K theory? So I suppose you are in the Kirchberg-Phillips setting.
Yeah,
so you have
the
SPI algebras.
Yeah, Kirchberg-Phillips is the old classical one. I don't have this theorem for all contracting groups. I think it's true. I have it for some classes. For instance, for iterated monodromy groups of complex rational functions. So you have the same in that case. And that's using Kirchberg-Phillips for the whole thing, for the Kuhn-Pimsner algebras. But for the 0 degree, it's also true for the 0 degree. Because by new results, all these examples have finite dynamic asymptotic finite asymptotic dynamic dynamical asymptotic dimension is finite, so they all belong to this classifiable class of algebras of the more modern one, and also you can also do it for the 0 degree. That's the same algebras. Yeah.
And so relate. I mean, it's not exactly the same, but I wondered a related thing. You know, in Katsura's algebras, which I mean are related to these algebras in the sense that they come from self-similar actions of groups of Z on a graph. Katsura gives a condition that guarantees that the algebra is that his algebra is simple, purely infinite. And then he shows that with the K theory of these algebras, he covers all possibilities for SPI algebras and concludes that every Kirchberg algebra is isomorphic to one of these. So, in particular, if you find a Katsura algebra that happens to be SPI, then it is isomorphic to one that satisfies his conditions. But something that I wonder for a long time is whether, I mean, if I have one of these algebras that I know is simple, purely infinite, then it should be isomorphic to one that satisfies his conditions, and whether this can be seen, can be made explicit, and even I mean, maybe too much to hope for that it be algebraic, so that it appears already at the Steinberg algebra level. But has this kind of problems ever appeared in?
I don't think it's possible in these cases. Well, say in the other picture coming from the dynamical system, the groupoid can be connected. I mean, it's locally connected, so the Steinberg algebra will not work at all. So it's definitely not I don't think you will see it algebraically. It will be hard.
Okay. So Mike Whitaker has raised his hand. Please.
Yeah, I guess I just wanted to add to that answer that you need infinite graphs to do the isomorphism for Ketzer algebras. So it's a different setup, I guess.
Yeah. I say here these algebras are very far from being general. The K0 depends only on dimension well, they're definitely very special K0 and K1 in this case, K0s in this case. So this is very far from being universal. It's a very special class of algebras here.
Yeah.
That I'm talking about. One more thing that doesn't appear in our paper, but all this can be applied and works for a slightly more general setting of contracting self-similar inverse semigroups. So all these statements that I mentioned. But we didn't write it because, yeah.
So you mean the universal groupoid of such a inverse semigroup?
Well, contracting self-similar inverse semigroup, it's a slight generalization of contracting groups. They appear as, say, tiling semigroups of self-similar tilings, like Penrose tiling, things like that. They are very similar, and there you also have the same arguments would work, but it's
So are there any other questions? Otherwise, I shall stop the recording now.